Transformations of exponential and logarithmic functions. So first thing is with an exponential and a logarithmic functions, these are inverses of each other. So they're basically reflections of each other over the line y equals x. And so what an exponential function does is it raises a number to the value of x. So for example, we have what we like to call the parent function of an exponential is y equals 2 to the x power, or in general, any number raised to the power of x. And so y is equal to b, which is the base, to the power of a number. And so if we create a table for this function, this will be 2 to whatever x is. So 2 raised to the negative 2 power is really 1 over 2 to the positive 2, which is 1 over 4, which gives us 0.25. And you can do the same thing with 2 to the negative 1. 2 to the negative 1 is really 1 over 2 to the first, which is just 1/2. So negative exponents really create fractions. And so now we're at 0.5. Well, 2 to the 0, anything to the 0 power, so 2 to the 0 is just going to give us a 1. 2 to the first is 2, 2 squared is 4, and 2 to the third is 2 times 2 times 2, which makes 8. So if we were to graph this, we would have negative 2 and like negative 1/4, negative 1, negative or positive a half, sorry, 0, 1, 1, 2, 2, 4, 3, 8. And even if you wanted to do 4, 2 to the 4th power would give you a y value of 16. And so the way this graph looks is it starts kind of on the bottom left. But here's the thing. We actually have another boundary line for this function. We have a horizontal asymptote. So we have a boundary that this line will never cross. So in this case, our asymptote is horizontal. Now, the reason why it is horizontal, no matter what number you raise a number to, even if it's a negative, you will never get a 0 as a result. We can see why if we look at the full table of values. So if you look here, we have a 2 to the x power graphed on the graphing calculator. And if I look at these values over here on the table, and I look at my x's and I keep track of where my y's are going. So if I move down the table, my x's are getting larger and so are my y's. But if I move backwards on the table, so my x's are going to get smaller, negative 1, negative 2, and the y's are also getting increasingly small. However, you'll never hit 0. I just get smaller and smaller and smaller. So now I have 2 decimal points as zeros instead of there's 3 decimals of 0. There's 4, 5. Now here's the thing. It's going to look like it hits 0. So this number right here, let's see if I hover over it. There it is. That says 9.536 times e to the negative 7. That means there are 7 decimal places to the left of that 9. So no matter what x value you raise a number to, it will always give you a positive y value back. And so that is why we have a boundary line horizontally at the line of y equals 0. Because there will never be a number of x that will result in a 0. And so for my domain, I can always have any number that I want. Let's fix our graph first, I suppose. So this graph is going to curve upwards forever. It's going to move left forever, but it's not going to go underneath y equals 0. So I can have every x value possible. It's just my range that is restricted. So because y is not ever going to be a 0, I will have 0 with a parenthesis and then up towards infinity forever and ever this way. So I can have the positive y values, I just cannot have negative y values or 0 for an exponential function. Now let's talk about a logarithmic. So what a logarithmic function does is it's kind of the opposite of an exponential. That's why they're inverses. So a logarithm finds the exponents needed to make the base equal to whatever x is. So it's going backwards. Exponential functions raise a number to a value. Logarithmic functions finds the exponents that need to make the base equal whatever x is. And so if I look at my example here, I have y equals the log base 2 of x. That's how you say that. The log base 2 of x. There's little pretend parentheses around that x. And so in this case, y equals the power of b, the base, to create whatever x is. So let's start with something a little more intuitive than, let's say, some fractions. Let's start with maybe a 2. So, and I realize I skipped a number here, but that's okay. If I make x 2, so what that would be is that would be y equals log base 2 of 2. So here's what this question asks. What number do you have to raise 2 to equal a 2? So basically, 2 to what power gives you a 2? This is the value of y. Well, what power will go in there? That's going to be a 1. We can try it again with one that doesn't have as many 2's. So if we do y equals log base 2 of, let's say, 8. So again, y will be 2 to the what power gives me an 8. That's what a log is. That's really the question that it's asking. Well, I know that the value of y that results in an 8 is going to be 3. 2 to the third power gives you 8. And so now let's look at what our tables look like. Let's kind of compare these two. On my exponential, my x's went from -1, -2, -1, 0, 1, 2, 3. Look at your y's on the log. They're opposites. The x's in the exponential is the y's for the log. And on the y's for the exponential, that is our x's on the logarithm. So let's see what this graph looks like. So we have a 0.25 as x. So here's 1. So 0.25 is a -2. So way down here. 0.5 is -1. A value of 1 is 0. X of 2 gives you a y of 1. An x of 8 gives you a y of 3. And I'm going to fill in the point that I actually missed. So right here, there's another coordinate. An x value of 4 gives you a y value of 2. And a x value of 16 is a y value of 4. So if I look at the way that this graph is going, it's starting at the bottom, kind of going right along the y-axis, and then it starts to bend away out to the top right. So we have another boundary line here on the y-axis, so a vertical asymptote this time. And so this one has the vertical asymptote at x is equal to 0. So again, since I cannot get an exponent to make a result of 0, that means that there will be no exponent to give me a result of 0. It's not possible. 0 will never be log base 2 of x. No matter what you put in here, I will never get a 0 as a result, no matter what I try to do. Now let's talk about domain and range for this guy. So domain, again, since my x has to be greater than 0, I do not include the 0 and it goes out to infinity. I can have all the x's as large as I want, I just cannot use negative x's. So you will never see log base b of a negative something. You'll never see that. This is not possible. You cannot have a negative argument inside of a logarithmic function. In the range, well, I can have all my y's. My y goes down forever here and up forever here. So all of the y's are possible from negative infinity to infinity. I just can't have negative in the inside of a logarithmic function. Kind of like you can't have negatives inside of a square root function. And so when we talk about transforming these here in just a minute, the asymptotes will also be translated up or down with the function if a translation occurs. Vertical translations affect horizontal asymptotes. Horizontal translations will affect vertical asymptotes. So if you move a graph left to right, that's going to mess with a vertical asymptote. If you move a graph up and down, that messes with a horizontal asymptote. So let's talk about transformations. So again, we have this diagram for us to follow. This is the same diagram you've seen all year long. So let's go ahead and jump into an example. So the graph of f of x equals 2 to the x is transformed to create g of x equals 4f of negative x plus 3 minus 2. So letter A says describe the transformations that occurred to f of x. Well, let's get our pieces. So I see that this 4 is in the same place as A. So that means A is a 4. So what that does is that creates a vertical stretch by 4 because 4 is larger than 1. So this has been vertically stretched by a factor of 4. So my graph is going to be taller this way. It's going to be pulled up and down vertically. I also see that there is a value of b. b here is -1. Well, because it's a -1, we don't really have a compression or a stretch in this case. We just are reflecting over the y-axis. So what that means is instead of going from the bottom left to the top right, like it usually does, we're actually going to flip over, and now we're going to be going top left to bottom right. This guy here, the x plus 3, that's our c, so that's going to be a shift left 3. And then -2, that is the d parameter. Whoopsie, -2, not minus d. -2. And that means we will be shifting down 2. And that is the verbal description of the transformations that occurred to create f to g. So let's look at the graphs. Let's try to find the correct picture. So if we remember our parent function, it goes like this, and it always has a y-intercept at 0, 1. That is the parent function of any exponential, has a y-intercept at 0, 1. So this is what the parent function should look like. And so let's think about reflections and stretches. So if I stretch it vertically, that means it's going to shoot up a lot faster. So I'm going to take the ends and I'm going to pull it top to bottom. If I reflect it over the y-axis, it will actually be looking this direction. So it's still facing upwards, but it's going from the top left to the bottom right. So this graph here is actually upside down. This guy had a reflection over the x-axis, which is incorrect. Now let's look at the movements. So I should be moving left 3 and down 2. Well, this graph is to the right of where my parent function should be. So here's kind of where the parent function should be. And so that is incorrect. I moved to the right, not to the left. This guy also, so again, here's kind of where the parent function should be. This guy moved to the right, not to the left. That is incorrect. And here's where the parent function should be, give or take. This moved to the left, and it moved down 2. If you look at the asymptotes, here's the old asymptote, and here's the new one. And that works out just fine. So this first graph is the correct graph of the transformation. Well, the asymptote moved with it. So if I moved down 2, that means my new asymptote should be at y equals -2. Because it's exponential, it's a horizontal asymptote, not a vertical one. The domain, well, it's still moving furthest left to furthest right, so we're still good there. So -infinity to infinity. The range is going to change, however. The lowest value I can touch is going to be this horizontal asymptote at -2. But it has to be a parenthesis because I won't actually ever touch a value of -2. And then my highest y value goes up forever. So pause the video and see if you can try example 2 on your own. And here's your solution for example 2. So the negative in the front is our value of a, which reflects over the x-axis. So if my parent function should look like this, and I reflect it over the x-axis, I now have a exponential that is facing upside down. The b value is a half. So what that means is you have a horizontal stretch by 2. We're going to take that 1/2 and flip it over. I need the reciprocal to see how much it's horizontally stretching or compressing. X -2 on the inside means you're moving to the right 2, and +3 means you're moving up 3. So if I look at all of these graphs, well, the ones that are flipped over are the middle 2. These guys did not have a reflection over X, they had a reflection over Y. They're backwards. Then this one here, I should be moving down, up 3 and right 2. This guy had me move down 3 and not to the right. So this was incorrect because it went the wrong direction. So here's where my new y-intercept would be. And if I went up 3 and right 2, here's my new graph. There it is on my line. Now for the y, or the asymptote, we have it at y equals 3 now. The up and down controls where the asymptote is going to be. So originally it should have been at 0, but if I moved up 3, That means my new asymptote is at y equals 3. Domain is still all real numbers, furthest left to furthest right, but my range has now flipped. The lowest value of y possible is negative infinity. The highest possible value of y is up to 3, but not including 3, which is why it has a parenthesis. Let's look at some logs. So the graph of f of x equals the logarithm of x is transformed to create g of x equals 1/2 f of negative x plus 2 plus 3. So letter A, describe the transformations. So far this is no different than exponentials. This is still my A, and because it is less than 1, we have a vertical compression by 1/2. This is the one that stays the same. The negative on the inside means we will reflect, that's our B, over the y-axis. So let's think about what that's going to make it look like. It should be, my parent function should be on the right-hand side at this point at 1, 0. So if I'm going to reflect over y, that means I now have this coordinate at negative 1, 0 instead. It's going to flip over the y-axis, and that means it's going to look something like this. Then we have x plus 2, which means we are shifting to the left 2, and plus 3 means we are shifting up 3 units. So now we are needing to select the correct graph. So again, let's look at our reflections and stretches first. So a vertical compression means we are squeezing this guy down top to bottom. So this little guy is going to be a lot flatter than the parent function. We're squeezing it down. And it needed to reflect over the y-axis. So it needs to look something like this, pointing to the left. So this guy here is not pointing the right direction. He was not reflected correctly. The second one is incorrect. Now let's look at left 2, up 3. So I always like to track an intercept, track a point. So I should have a coordinate at, let's see, negative 1, 0 here. And if I move left 2 and up 3, so left 2, up 3, I do in fact hit the graph, so we're good there. That's a possibility. Here's where my point used to be. If I go left 2 and up 3, well, this one's incorrect. That point did not land on that graph. Here's where I should be. If I move left 2 and up 3, I hit the correct point. So far, the first and the last graphs are okay. We need to think about that vertical compression. So I need my graph to be flattened, compressed down. So this guy's really flat right here. This one still has quite a bit of a curve on it. So this guy has my vertical compression. The first one does not. So the last option is the correct graph for this transformation. Now let's talk about the asymptote. The asymptote should be right here at x equals 0. Well, let's think what happens. If I move up 3, if I used to have my asymptote here at up and I move it up 3, well, that's not changing anything if I just move it up. But when I move it left 2, that's going to bounce it 2 to the left, and now it has moved, and it is now x is equal to negative 2. So again, up and down shifts affect horizontal asymptotes. Left and right shifts affect verticals. So let's look at domain. So my domain, my furthest left is going to be negative infinity forever. So negative infinity. The furthest to the right I'm allowed to go is that boundary line at negative 2 with a parenthesis because I cannot actually include the boundary line itself. Range, the furthest bottom is negative infinity. Furthest up will also be positive infinity, just really, really slow, but it'll get up there eventually. So for number 4, we do have a logarithm. It just does not say log. So we have f of x equals ln of x. Well, this is the natural log of x. So that's how you say this. It's kind of backwards. Natural log, ln. And so when we transform it, it works the same way. Negative natural log of, this is all the stuff that's inside, 2 parentheses x minus 3, and then on the outside we have plus 2. So to kind of help you out a little bit, let's label these guys together as A, B, C, or D. Well, the one out front is usually the easiest. That's our A. The number multiplied inside parentheses is our B. Here we have C. And added or subtracted to the outside is D. So pause the video, see if you can try example 4. And here's your solution for number 4. So also, instead of tracking a point, you can also track an asymptote. So if we try to track the point 0, 1, or 1, 0, excuse me, like we did before, we would have to go right 3 and up 2, but I don't land on my graph. Well, the reason is this horizontal compression. That's the reason why you don't quite end up on the graph like you're supposed to. So instead, we can track an asymptote. So the asymptote should be here at x equals 0. Well, let's see. If I move the asymptote 1, 2, 3 to the right, just like I'm supposed to move everything else, we end up with the correct asymptote on this graph. This guy here was moved left, not right. Let's do some writing of equations. So number 5, let the graph of g be a reflection over the y-axis followed by a vertical stretch by a factor of 6 and a translation 4 units left and 2 units up from the graph of f of x equals 2/3 to the x. Write a rule for g. So writing a rule for g simply means write out an equation for the new transformed function. So let's see what happened. So it says that we had a reflection over the y-axis and then we see followed by. So the reflection over the y-axis must be done first. So reflecting over y, that is our b parameter, and that makes b a -1. So when we write this, our first transformation, g of x, will be 2/3, but then we need a -1 times x. There's our first transformation. Then it says followed by a vertical stretch by a factor of 6. Well, that's our a. Vertical stretch by a factor of 6 is a. So our new function for step 2 will be a 6 times the entire 2/3 to the -1x. Now, luckily for us, there's nothing added or subtracted to this function, so we simply have 6 times 2/3 to the -x. Next we have it said it was a translation 4 units left and 2 units up. So 4 units left is our c. So that'll be an x plus 4 because left is always backwards than what it says. 2 units up is the d parameter, and that will be a plus 2 at the end. So our final transformation will be 6 times 2/3 to the negative parenthesis, because when you do c, you're taking this x out and you're replacing it with x plus 4. So the negative needs to go on the outside of a set of parentheses inside that exponent. So it is a very busy little exponent. And then plus 2 out on the end for our d parameter. Pause the video and try example 6. And here's your solution for number 6. Please remember, when you apply an a, it has to be multiplied to the entire function from the previous step, which includes the -1. So this needs to be distributed out to both the e here, and the 1/3 times -1 creates a -1/3. Example 7. Let me cross this off here. It's example 7, not example 5. If f of x equals log base 2 of x and g has been reflected over the x-axis with a horizontal compression of 1/3 followed by a translation 9 units right and 4 units up, what is the equation for g of x? So let's see. First things first. It says it's been reflected over the x-axis and has a horizontal compression of 1/3. So we have two things to do first. So a is a -1, that's that reflection over the x-axis. And a horizontal compression of 1/3 means our b is actually 3. So our first step for our new function g of x will be a -1 times the log. And when I do my logs, I always like to do a cursive L. The reason is that way my 1's and my L's for log doesn't get mixed up. So -1 log base 2, make sure it's a little bitty 2 at the bottom, of, and then b is 3, and x. There's our first set of transformations. Then it says followed by a translation 9 units right and 4 units up. So c is the 9 units to the right, x minus 9. d is our 4 units up with a plus 4 at the end. So our second set of transformations will be a negative log base 2 of, and remember, 3 has to stay on the outside of another set of parentheses because this x gets replaced with the entire x minus 9. So now we have 2 parentheses instead of just 1. And then our d is plus 4 at the end. Pause the video, try example 8. And here's your solution for example number 8.